Well, hello, retro computing enthusiasts. Mike here. Welcome back to my channel. And today I would like to show you my S-100 prototyping board that I've just built. And I put a little test circuit on it and plugged it into my S-100 box and was able to get this thing up and working. And I thought I'd talk a little bit about how I built this because those of you out there who are still running S-100 boxes, you might find something like this very useful. And as far as I know, nobody's selling anything like this out there, so you probably have to roll your own, and it's really not that hard. So I'll explain how I built this, what parts I used. I'll put links to everything in the video description, and you could build one of these yourself if you wanted to. I have a lot of plans for my S100 box, and I would like to prototype some circuits before I commit them to actual circuit boards. So I thought, well, why don't I build myself just a prototyping board where I can breadboard stuff, plug it into the box, and see if it works before actually committing it to an actual board. And well, it was surprisingly easy to build. So let me show you how I did it. I started out with one of these. So this is just an S100 prototyping board. You can get this from s100computers.com. Again, there will be a link in the video description to where you can get all these parts, including this board. Now, this one is just a bare board. It's got a big prototyping area on it. So this is what I will likely use to permanently build the circuits once I'm done prototyping on that. So this is just a prototyping board. It has places for, I'm only using the 5 volts, but it has, minus 12 volt, minus 5 volt places for those regulators if you need them. It's fully buffered. There's a line of buffers down here, which you can see I have populated here. They buffer control signals, data, address, more control signals, and high order address bits above the first 16 if you need them. I didn't populate that with the buffers because I don't need the higher order address signals. I'm using a Z80 system here. It can only handle 64K. So I didn't bother populating that. I started with just this. I put in the buffers. I put in the 5 volt regulator. I don't need more than 5 volts for any of the circuits I'm going to be doing. And I was ready to start building, on this board when I thought, you know what? Why don't I just stick some solderless breadboards on there and prototype my circuits and make sure they're going to work before, actually soldering them into one of these, because it's going to be a lot easier to debug and modify before I do that. So I thought, well, okay, I can just stick some solderless breadboards on here. They're adhesive backed, so that's easy enough, peel and stick. Then I thought, well, how am I going to get the lines on there? So I was looking around, and I found some short pieces of sort of breadboard material here on Adafruit, and I can solder them in to get all of the control, data, and address lines down there and make them available again with solderless. I can just push a jumper wire in there and run it to wherever it needs to go to get my control, data, and address lines wherever they need to go. Also did one for the power and the ground here. Again, I'm only using 5 volts, so I've only got plus 5 and ground here. But I could have put in other voltages if needed. So it all went together pretty good. I mean, there are a few issues here. The pins on the bottom of these were too fat to go through the holes, and I thought, well, I can either drill the holes out bigger, which is what my original plan was, but I thought, well, you know what? Let me just try something. So I just crushed the pins down with a pair of needle nose pliers and made them smaller, and then they went through the hole, and I just soldered them in. There's also some mounting pins on the bottom of these things I had to cut off so they sit flat and flush. So again, I could have drilled holes for the mounting pins to go through the board, but I'm like, nah. I don't want to drill any new holes in the board. I'll just clip the pins off. So that seemed to work. So also I had to cut down the boards a little bit. I wanted as much prototyping space as I could get here. But up here I had installed, the board comes with a place to install a power LED and a dropping resistor up there. And I thought, well, that's a nice feature. I'll just leave that on there. But I had to cut out part of the power rail here on the side of the board to make that work. And also I had to shorten this board right here and this power rail so that they didn't stick out too much. And as you can see, they're not quite aligned perfectly because the heat sink for the power transistor or the power regulator over here is in the way. Again, I could have run this over further probably and just cut the power rail, but I said, oh, what the heck, it doesn't matter. I've got plenty of prototyping space here. So I don't really care. It doesn't bother my OCD too much that they aren't perfectly aligned with each other. So anyway, it all came together pretty easily. I had already assembled the one prototyping board. I'd already put in all of the buffer chips, socketed them, and put in the power regulator and the LED for the power indicator, and some decoupling capacitors. So that was all assembled. So all I did was peel and stick everything else on and solder these in, and I had to bridge everything, because one thing I don't like about these prototype boards is there's no connection between the buffer chips and anything up here. You have to make your own connection. So basically, it's kind of the ugliest part of the board here. I had to jumper everything over myself, but I got it all working. I also ran power and ground over to my one solderless power and ground provider, and a couple of control signals that are not brought out anywhere. I have put little headers in there sticking up that I can put that I can stick female DuPont connectors on. There's one here for the master reset too. These are for driving the buffers for the input and the output on the data lines. These two up here. Now they did provide places to put in headers for the master clock and the power on clear. So I put headers in there too. So this board has some pluses and some minuses. There's if you look around on the site, I'll put a link to where I got this board. There's another version of the prototype board made up by another guy, which I think might work better. And I'm thinking about buying some of those too. So we'll see down the road, especially when it comes to permanently soldering my circuits together. I think I might use the other type of prototype boards rather than these. So we'll see how that goes. But I mean, I think for prototyping circuitry, this is perfect. This works great now. This absolutely works great. I've just got a little circuit on here. It doesn't do much. Basically, it's just it's just an I/O port, okay, that I can write to from the processor, and I can write a number to it, and the number will be displayed on this LED bar graph over here. And I just wrote a simple little program that outputs a number, delays, outputs a number, keeps counting up, counting up, counting up, and you'll see the whole display go over time. And just to make sure that everything was working and that I understood the S-100 bus signals and protocols here and could get this to work, because I've never really designed and built a card before that will interface to the S-100 bus. It's all been theoretical, but I just wanted to make sure I could get it to work, and it worked. So let me pop this into the box and we'll watch it work. And then we'll talk about, a little bit about the schematic for this and the code that drives it. But really, that's not as important as the fact that, if you need one of these, you can build one of these fairly easily. Okay, so let's get this popped in and get a look at it going. So here's the prototype board installed in my S-100 box over here. I got my Teletext System Master single board S-100 Z80 computer over here running everything. I have a long playlist on dealing with the Teletext System Master and everything I've done with it over the years since I've had it. But here's the prototype board installed, and as you can see, we are counting least significant digit up to most significant digit, and it's working. So yeah, it's working exactly like it's supposed to. There's the little LED up there that tells me I've got 5-volt power, and it's just happy as a clam here in my S-100 box, and I can prototype much more complex circuitry than this on it, which I intend to do in the future. I think next I'm going to work on a ISA hard drive interface for this computer. And I will prototype it on there before committing it to one of the other Proto boards in solder. So make sure it's working. Anyway, let's take a quick look at the circuit and the code that drives this for anybody who's interested. But I think the star of the show is the board itself, really, not what I built on it. But still, we'll take a quick look. Okay, before we get started looking at the code, I'll just say a quick word about my desktop background here on my computer, which I've gotten several questions on after the last few videos. So let me show you the picture without all of the icons in front of it so you can see the whole thing, and I'll explain what it is. Alright, so this is my wife and myself, and we are, when this photo was taken, we were in Nebraska in the White River Badlands fossil hunting. We're up on top of a hill. Looks like a real moonscape up on the hill here. There's a nice little valley down here with some trees, and this was autumn, so the grass was brown, but this can be quite green during the summer when it's raining. And there's a lot of livestock down here in this valley. But we were fossil hunting out in the White River Badlands. It was chilly, so I've got a jacket on. And I have found the skull of an oreodont, which was an ancient animal that lived about 30 million years ago in this area of the U.S. It was a weird animal. It's kind of the kind of weird mammals that lived between the end of the age of the dinosaurs and modern mammals. And the best way to kind of describe it would be like a cross between a pig and a goat. All right, and it kind of lived a weird lifestyle kind of in between those two types of critters today. So, yeah, so we're putting a plaster jacket on the skull I found up there, and my wife's helping me. She's quite the fossil hunter in her own right. In fact, I learned my fossil hunting skills from her. It just so happens this picture was taken. I found something interesting. So she's actually the expert fossil hunter, and well, I've been doing it for enough years now that I'm getting pretty good at it too. But she's helping me put the plaster jacket on my oreodont, and then we're going to dig it out and flip it over, and we have this out in our garage. And someday, when I'm too old and decrepit to traipse around on these moonscape hills here anymore, we'll get out all our plaster jackets that we've got accumulated out there in the garage, and we will start prepping the fossils that we have inside them. So anyway, that's what this picture is. It's one of my favorite photos. It was taken by a friend of ours, Mike Searle, who's actually the leader of the fossil hunting expedition. He came across this while we were plastering up this jacket, and he took the photo, and it actually made the cover of the Fossil Chronicles, the newsletter of the Tampa Bay Fossil Club. And this was one of our most successful and most fun outings in Nebraska, although I've loved all of them. They've all been a blast. Okay, enough of that. Let's get back to business. All right, let's take a quick look at the circuit I've built on the breadboard. It's fairly simple. It's 3 IC chips. We've got 74LS00 quad NAND gate. Got a 74LS138 3-to-8 decoder, and we've got a 74LS273 octo latch. And so we just got 3 chips on there. That's not counting the buffer chips and voltage regulator that are built onto the board. So basically, those are there too, but they're always there no matter what you build. So it's a fairly simple circuit. I've got S-100 interface over here, I'm calling this, And basically this is a bunch of lines coming in from the S-100 interface. I'm only using some of them. I'm not using a lot of them. As you can see, there's a lot of them X'd out here, not being used. We're only using the upper four address lines, A4 through A7, and those are going into the 74 LS138 3 of 8 decoder. And the way this is going to work, this is going to decode the address range C0 to CF. So pin 11 of the 74 LS138 should go low when we have anything in this address range coming in. And you may think that's a little wasteful to decode 16 addresses just for one latch. Well, I have plans for the future. I'm working on something that's going to use most of the 16 addresses in that range. And this is just a quick test to make sure I understand how the S-100 bus works and that I can decode things the way I want and get things working. So that's just a quick test. In fact, the address decoding is going to be a little more complex because I'm going to have stuff that I'm going to reading and writing to. And, I don't want to have bus conflicts. So, yeah, it's going to be a lot more complicated in the doohickey I want to build. Yeah, but for now, just to write to a latch, it's pretty simple. I'm taking the S out line from the S-100 bus and I'm inverting it. Using one of the NAND gates here as an inverter, and I'm feeding this into one of the enable lines on the 74LS138, and this is going to give me an IO write signal coming out here when we are in this range. When the Teletext System Master, the main computer in the box, is writing to this IO address range, we're going to get an IO write signal coming out of the 74LS138, and I'm feeding that right into the clock input on the 74LS273, and we're going to get a low going pulse coming out this way. Now, some of you may be thinking, well, wait a minute, this 273 needs a high going pulse to latch. Yes, well, this is going to go back high eventually once S out is no longer asserted, but the data on the data bus is still good for a little while. So this will go high again and it will latch the data on the data bus at that point, and then it's just going to display it. We've just got we just got an LED bar graph here, a 10 LED bar graph. I'm only using 8 segments of it, and a resistor network here to limit the current, and that's it. That's the whole circuit, just the little test circuit to make sure my prototyping board in there works. And it's working good. We'll take a quick look at the code too. There's not much to it either. Pretty simple code here. As usual, we are at asm80.com, my favorite online compiler for retro processors. Support this website if you use it. I have made a big donation to them via PayPal, and I encourage anyone else using this website regularly to donate to them so they can keep it running and they can improve it. They're working on a rewrite of this with some new features. So yeah, if you use this, donate to them to help keep it working, okay, and make it better. Anyway, okay, pretty simple code. Its org is going to be at 8,000. So basically, what I'm going to do is I'm going to import this. Once I have the computer up and running on its monitor program, I will import this as a hex file to 8,000 up in memory, up into the upper half of RAM memory. And I'll just do a jump to it from the monitor and let it run. And it's just going to run in an infinite loop until I reset the computer. So what we're going to do here is we're going to XOR A, which basically sets the accumulator to 0. It's a quick and easy way to set the accumulator to 0. Let's see, we're going to output A to the port address, and port address is defined up here as C0, although any port from C0 to CF would write to that latch. And then we're going to call a little function called delay down here. What delay does, well, we've seen delay before. It's part of the code that I use. Well, I use it extensively in the Naboo. I'll put a link to my Naboo playlist in the upper right if you haven't seen that. We use delay for a lot of things on the Naboo, but basically what it does is it just, we're going to push AF onto the stack so we preserve its value. And we're going to load the HL registers with delay count, which I define up here as 7FFF. And we're going to decrement HL, and then this code down here checks to see if HL has reached 0, because there's really no good way to tell on the Z80 on the 16-bit register when you decrement it whether you reach 0 or not. It does not trip the 0 flag. So you have to do a few gymnastics to figure that out. We're going to load A with the L half of the register, and then we're going to OR it with the H half of the register. And if that mathematical function goes to 0, we know that the HL register is 0, and that will trip the 0 flag. But if it's not 0, we will jump relative on not 0 up here to D-loop, and we will go through this again. We'll decrement the HL, and we'll just keep doing this until HL does get to 0. So that's what gives us our delay. And we're going to do through this loop about 32,000 times. All right, and that'll give us enough delay that the lights, we can see the lights blinking one after another, okay? If you don't do a delay, well, the lower order bits are just going to look like they're on all the time because we're counting so fast. Even on only a 4 megahertz Z80, it's that fast. And then once we do reach 0, we're going to exit this loop. We're going to pop the AF register off of the stack, and we're going to return, come back up here, we're going to increment A, and we're going to jump relative back up here, and we're just going to output A again, call delay, wait, increment A, come back up here, output A, and so on. And this is how we get our count up, you know, on that's being displayed on the LED bar graph. So that's pretty simple little program. I mean, it's running under the monitor. You know, got to have the monitor running to do this, but we've talked about the monitor in the past. That's a big complicated piece of firmware, but this little program, you know, once you got the monitor running, you can just import it into upper RAM and jump to it from the monitor, and, you know, it'll, like I said, it'll run until I reset the machine, just in an infinite loop. All right, I hope that's understandable. Leave a comment, leave a question if there's anything you don't understand about what I did. Any questions you might have about how I built the board, about how I built the circuit, about how the software works. Just leave me a comment, leave me a question, and I'll do my best to answer them. Oh, and before we go, just a reminder here that a while back I put out another video on building prototyping cards, this one for the Naboo. So if you have a Naboo computer and you want to do some hardware prototyping, I have a video on how I built a plug-in card for the Naboo that you can prototype circuitry on. I will put a link to that video in the upper right. If you're at all interested, check it out. This was even easier to make. So there you are. That's how to build this breadboard prototyping board for the S-100 bus. I hope you guys found this video interesting, enlightening, educational, inspirational, informative, whatever. Give it a like, give it a thumbs up, and subscribe to see my future videos. This board will likely appear in future videos as I prototype new and better circuits on it in the future for my S-100 box. And subscribe to see those future videos and all the other videos that come out on this channel about electronics and retro computing. And I'll see you in the next video. Thanks a lot for watching this one. Bye.